So if contingent links happen to execute early, some constraints will go away. Instead of talking about the consistency of an STN, we talk about the dynamic controllability of an STNU. So a dynamically controllable STNU, well, it gets a little complicated. We're not just looking for a solution. Instead, we want a strategy, a dynamic strategy. Now, what does this strategy control? It controls the non-contingent time points. We don't control the execution of the contingent time points, at least not directly. But we do control the non-contingent time points. So the strategy is for when we execute the non-contingent time points, such that all the constraints that we want to satisfy will be satisfied, no matter how the contingent durations turn out. And the key thing down below is that you can react to observations. If you see that C executes early, then you may want to change things and execute B early. But as long as C remains unexecuted, B has to wait at least 4. But if C executes early, B can execute early. So it's a dynamic strategy. It can respond in real time to executions that it observes of these contingent time points. So if you get out of the taxi cab early, you might want to buy a sandwich early. So here we go back to this example, and we'll see where this red arrow comes from. But the way this red arrow is interpreted is that as long as C is unexecuted, B must wait at least 4 units after A. So it's a kind of conditional constraint. I hesitate to use the word conditional because that has a different meaning in conditional temporal networks. But it's a kind of a conditional constraint. The idea is that as long as that condition C is unexecuted holds, then that constraint has to be satisfied. B has to be at least 4 after A. But if C executes early, then it's no longer unexecuted. That constraint disappears. Okay, so how do we figure out what's the analogy to a distance matrix for an STNU? Or, you know, these negative loops that we saw in STN graphs that were so important. Well, the corresponding thing in an STNU is what's called a semi-reducible path. And I'll tell you what a semi-reducible path is. But if you think about an STN graph, the strongest constraints were those shortest paths. In an STNU graph, there's a corresponding kind of path. It's not every path, but there's a corresponding kind of path called a semi-reducible path. And those paths correspond to the strongest constraints that any dynamic strategy must satisfy for an STNU. So we'll put off for a second saying what a semi-reducible path is. Just be aware that it's not every path. After all, if you think about the lowercase, uppercase loop there, that's not a semi-reducible path because you can't have the lowercase and uppercase bounds possibilities being encountered in the same scenario. So that's not a path that represents a constraint that the STNU, that the strategy would have to satisfy. And then, by analogy, instead of the distance matrix D, we have the all pairs shortest semi-reducible paths matrix, D star. Okay. So not the shortest path between every pair of time points, but the shortest semi-reducible path. Okay. So this is the corresponding fundamental theorem for STNUs. So if the things are equivalent, the STNU is dynamically controllable. In other words, there exists a dynamic strategy that's guaranteed to safely execute it. G has no semi-reducible negative loops. That's the analogy, the corresponding feature to negative loops in an STN graph. And the all pairs shortest semi-reducible paths matrix has non-negative values down its main diagonal. If you find a semi-reducible negative loop in an STNU graph, then it's not dynamically controllable. Okay, now there's been a lot of work, a lot of improvements, a lot of advances over the past many years mostly involving Paul Morris and colleagues. They started with, in 2001, what they called a pseudo-polynomial algorithm that depended on the granularity of the domain. So that was okay as a first step, but they, in 2005, presented a order n-fifth algorithm. N is the number of time points in the network. And then in 2006, went to an n4, order n4 algorithm. And then I was working on this, and some other people were working on this, and I gave a tutorial in 2013 where I raised the question, is there an order n cubed algorithm? Because I had showed that there are some nesting relationships between these semi-reducible paths, and it was looking like there might be an order n cubed algorithm. And in 2015, I sat down, well, it's time to do that. And then I said, well, I better check what Paul Morris is doing. And then, boom, there it is, order n cubed algorithm. But I wasn't the worst off. This other researcher had come up with an algorithm that was almost the same as Morris's, and it was published, like a millisecond later. But Morris has done the lion's share of the work on STNUs over the years, so certainly he deserves the credit. Always full of great insights. His papers are full of great insights, and a very clever and intelligent person, and he's really done the lion's share of the work on STNUs. So, order n cubed, that's the same as complexity as for STNs, which is a surprising result given that you have these contingent links with uncertainty. And not only that, we can flexibly execute a simple temporal network, one that's dynamically controllable, in order n cubed time overall. We'll have more to say about that. Okay, now, in 2009, was that a time warning? In 2009, I was troubled by the semantics that they presented in 2001. The semantics is confusing because it's in terms of complete schedules and complete situations. So a situation is when you know all of the durations of all of the contingent links. And it's a little confusing because you don't know that information during execution. So to describe dynamic controllability in terms of this information that you don't know at runtime was a little confusing to me. I did find a little error in their semantics, more about that later. But by fixing that error, I was able to provide an alternative characterization of what I call real-time execution decisions. So the semantics for dynamic controllability can be expressed by these real-time execution decisions. The idea here is that these RTEDs, these decisions, they tell you what the agent faces in real time, what kinds of decisions the agent has to make. I mean, think, you're responsible for when you execute these time points. You're the one coming up with a strategy. What are your options? Well, there's only two options. You can wait for some activated contingent link to execute. Right? So if you've already gotten into the taxicab, one of the things you can do is just wait for the taxicab to get to where you're going. Now that only is a reasonable thing to do if some contingent link has already been activated. Maybe there's 3 contingent links that have already been activated. Maybe you called somebody up and asked them to call you back, and maybe you got in a taxicab, and maybe you pulled the pin out of a hand grenade. I don't know. So you can wait for something to happen. That's one of your decisions. On the other hand, you could say, well, if nothing happens before time 10, then I'll execute X and Y at time 10. That's what we saw before. If nothing happens before time 4, I can execute B. That would be one strategy. Now, the thing is that if something happens before time 10, you can change your decision. But if nothing happens before time 10, you execute X and Y. Okay? So those are the 2 kinds of decisions that an agent can make during execution. So here's that example. Our initial decision is that if nothing happens before time 4, we'll execute B at time 4. Well, one possible outcome is that C executes at time 2. So you can react to that information. You can say, okay, instead of waiting till time 4, I'm just going to execute B at time 3. Now, the only possible outcome in this simple example is, since you've already executed A and C, B is going to happen at 3. But if you go back to your original decision, it may be, an alternative outcome might be that C doesn't execute before time 4. So if nothing happens before time 4, we execute B at time 4. And then your next decision is to just wait for C to execute. But the point is that any dynamic and viable strategy for executing a dynamically controllable STNU can be expressed in terms of these two kinds of decisions. Now, how do we get these decision strategies? Well, there's constraint propagation rules for propagating the constraints in a simple temporal network of uncertainty. Now, we saw that in an STN, if you have a path of constraints, then you just add up the edges on those paths, and you get an implicit constraint. Well, because we have these lowercase and uppercase edges, things are a little more complicated with STNUs. So here, well, this is the simple case, just like in an STN. If you have two ordinary edges, then they just add, their lengths add. But if you have an uppercase edge, then, well, yes, they do add, but you preserve that uppercase label. And you can think about this, you know, if C might not happen until time 10, and you want Q, the relationship between Q and C, you want C to be no more than 3 after Q, then Q has to wait at least till time 7. Because if you execute Q early, say at time 5, and C executes at time 10, you're out of luck. It's those kinds of considerations, playing out those scenarios, that proves the soundness of these rules. And I'm not going to, you know, explain each one of them, but, you know, in the lowercase example, it only applies if the right-hand edge is negative, and, you know, there's an asymmetry here because, you know, time only flows in one direction. You know? So in this case, with lowercase rule, you don't preserve the label. You get an ordinary edge. And you can mix the two as long as the two contingent time points, C and C2, are different contingent time points. Then you're not mixing the two opposite possibilities for one contingent link. So we get the cross case rule, and that preserves the right-hand uppercase label. And then there's a situation where you can remove the uppercase label. Basically, that happens because, you know, say that you're, as long as C remains unexecuted, you have to wait at least 1. But you know that C is not going to execute before time 1. The earliest C could execute is 3. So it's not a conditional constraint, it's an unconditional constraint. So you can remove the label. So it's those kinds of considerations that allow you to do these various kinds of constraint propagation. So you're preserving, in some cases, uppercase labels. So what does semi-reducible mean? So if you think about that path of arrows that's on the upper edge of this diagram, that's your original path. And if you apply these edge generation rules or constraint propagation rules, you get some of those implicit edges. Now, if down at the bottom you have a path that consists only of ordinary edges or uppercase edges, that's called semi-reducible. The original path is semi-reducible if it can be transformed into a path that has only ordinary or uppercase labels, ordinary or uppercase edges. And it's the semi-reducible paths, those are the ones that a dynamic strategy must satisfy for an STNU. The basic way to think about the lowercase edges is that they're only needed to generate these edges down here. Right? Once they've done all the constraint propagation with the lowercase edges, you can forget about the lowercase edges. They've done all the work they're there to do. Now, you will still have some uppercase edges. You'll have these weight constraints, these conditional constraints. And you have to keep track of those during execution. You know, if C hasn't yet executed, B has to wait until at least time 4. But if C executes early, that constraint goes away. So just to revisit the fundamental theorem, now that you know what semi-reducible negative loops or semi-reducible paths are, you know you find them by constraint propagation, and you can, once you compute all the semi-reducible paths, you can get the D star matrix, and you can do that in order N4 time using the 2006 algorithm. And there's the 2014 algorithm doesn't compute the all pairs shortest semi-reducible path matrix, but it does determine dynamic controllability. So how do we execute STNUs flexibly? Well, by analogy with the STN algorithm, you can only update the D star matrix entries involving Z to keep track of the lowercase and uppercase edges. You still have to keep track of which edges are enabled, which time points are enabled, and you also have to keep track of these weight constraints. But you can do that. The updates would be order n squared per execution event, or order n cubed overall. But in Morris's 2014 paper, he showed that he can derive the dispatchable form of an STNU using his order n cubed algorithm. And that work that I did in 2013, basically what it's doing is it's doing a dispatchable propagation, but it's using more edges than in the dispatchable network typically. So his order n cubed algorithm generates a dispatchable STNU. There's two differences during execution. You don't control when the contingent time points execute, so you just observe them when they execute. And there are these weight constraints that you have to keep track of. But there is an analogy to the STN dispatchability, and it's a great paper, as usual, with Morris's work. I'm going to skip these slides just because I'm flexible. Then I'll just say that the theory of STNUs has been advanced dramatically over the past few years. And as I've tried to stress to the ICAPS community, I think they are doing it, that STNUs are ready for prime time. And you know, Brian Williams and many folks here are using STNUs, incorporating them into their planning and scheduling applications, and that's great. Okay, what other kinds of temporal networks? Well, in 2003, Samardino's and others presented what they called the conditional simple temporal network. And the motivation here is that sometimes you do test actions that generate information. You control when you take the patient's blood pressure, but you don't control the result. So you may wait until time 25 to take the patient's blood pressure, and then at time 25 you find out what the patient's blood pressure is. And sometimes there'll be constraints that limit what you can do. If you don't know the patient's blood pressure, then you may have to be careful with what you do. You may not administer a drug. If the test comes out high blood pressure, then you may take one course of action. If it comes out low blood pressure, you may take another course of action. So the generated information is typically not known in advance, and some actions only make sense in certain scenarios. Now what we'd like to do, by analogy with the STNUs, is have an execution strategy that could react to these observations in real time. So there's many businesses, especially in Europe, that are using these workflow management systems to automate manufacturing processes. And one of the examples that I like the most, and I've worked with some colleagues in Verona, Italy on this, is the workflows are being used by hospitals to represent different treatment pathways for patients. And what we've focused on are how can we formalize the temporal foundations, dealing with time points and time constraints for these workflows in hospital situations. So what do we have in conditional STNs? We have, or CSTNs, we have time points and temporal constraints just like in an STN. But some of the time points are these special things called observation time points, like when you take the blood pressure. You control when you execute those time points, but you don't control the outcome of the observation. And then some of the time points and constraints can be labeled by conjunctions of propositional letters. So, you know, if you're doing 5 different tests, A, B, C, D, and E, maybe these 2 time points have to be separated by 100 seconds if A and B came out true, but C came out false. So what do we have? We have propositional letters, P, Q, R, S, T. Each propositional letter has a corresponding observation time point. Normally we write it with the same letter, just written with a question mark, uppercase. And then labels can have a conjunction of 1 or more literals. For example, P, not Q, R. Now a scenario would specify the values for all letters, the outcomes of all tests. And of course, you don't normally know this information at runtime. You only know the observations that you've seen so far. The real scenario is only revealed incrementally during runtime. And the time points and constraints can be labeled. So here's an example of a CSTN. Now I'm using the interval notation for the time constraints. So for example, from P question mark to Q question mark, that's got to happen between 15 and 20 minutes. But only if P comes out to be true. That constraint only applies if the test P comes out to be true. But if P comes out to be false, then you just go straight to Y, which is your exit point. Yep.
Can a time point give more than one truth value to different propositional variables?
I suppose it could, although I don't think you need to have that in the formalization. I think you could, for example, you could have 2 observation time points that were constrained to occur at the same time. So, yeah, and in the same way, you could have, instead of just having binary values, you could have, you know, any finite number of values. Yeah, that would be a nice generalization. Notice that the Q test is only done if P turns out to be true. So the label of the time point Q question mark is a P, saying that only do that test if P comes out to be true. If P comes out to be false, you don't do that test. So time points can be labeled, telling you in which scenarios they need to be executed, and constraints can be labeled, telling you in which scenarios they need to hold. Now, the literature on CSTNs, they use the term dynamic consistency, but you can think of it as dynamic controllability, just a different context. It's the same general idea. It's dynamically consistent if there exists a dynamic execution strategy that guarantees that all relevant constraints will be satisfied no matter which scenario is incrementally revealed over time. So it's the same idea as in an STNU, that the strategy can react to things that it's seen already, and you want to be able to satisfy all the constraints, no matter how the uncertainty is resolved over time. It's just a different kind of uncertainty. And then the execution decisions can react to observations. So there are many different ways of solving what's called the CSTP, the conditional simple temporal problem. You can convert the problem to a disjunctive temporal network, which is what the original researchers did. I don't know that they ever implemented that. It certainly was an exponential, these are all exponential algorithms. In 2014, Chamati and me and other people got together and showed that the CSTN problem can be converted to a time game automaton, and you can solve it that way. Again, that algorithm didn't turn out to be practical. We did implement it, but it wasn't practical. Komen and Rizzi, 2 other researchers at Verona, converted the CSTP into a hypertemporal network and used an exponential time algorithm for that. I think they have by now implemented it. We're going to actually implement all of these and work together to compare them. The one I'm going to talk about today is at the bottom, work that I did with Posanato and Combi, who are researchers at Verona also, and that's to propagate labeled constraints. And you can see this was just a couple of years ago. So it's a constraint propagation algorithm, but different kinds of constraints, different features, different things need to be handled. So we propagate labeled constraints, and where did this idea come from? Well, Patrick Conrad did work on Drake. Now this was in a different context. This was doing where the user makes the choices. In the conditional simple temporal network, the environment makes the choices. You determine when you do the test, but the environment or external reality or whatever you want to call it determines the outcome of the test. So different context, but the idea of having edges labeled by these so-called labeled values, well, that's where we got the idea from, and we ran with it, and different kinds of things came out. One thing was that constraint propagation, it was not enough to think about propagating consistent labels. You could have an edge labeled by P and another edge labeled by not P. They're not consistent, but you still have to propagate along them in certain times. So we introduced this thing called a Q-literal, which is represented by P question mark, and what that stands for is that P has not yet been observed. The value of P is not yet known. And a Q label just is like an ordinary label, except that some of the literals may not have been known yet. So if P is true and Q is false, and R hasn't yet been observed, and S is true, then some constraint may need to be satisfied. And there are different features in the graph we call Q loops and Q stars. So here's a labeled constraint. It's just like an ordinary constraint, except there's a propositional label here, L. And the idea is that constraint must hold in scenarios where L is true. Now keep in mind, you start off with the empty label as your scenario, because nothing's been observed yet. And then over time, you conjoin the propositions that you've seen so far. So you might see P first is true, and then Q is false, and then later on R is true. So we had 3 different kinds of constraint propagation rules, but there were 2 varieties of each. One that dealt with consistent labels and one that dealt with these new Q labels. Here's an example of the labeled propagation rule. This is just like ordinary constraint propagation. You can see 3 plus 5 is 8. But what happens with the labels is we just conjoin them. So we have PQ and Q not R. You conjoin them together and you get PQ not R. So for this rule, the label has to be consistent. The R0 rule, you know, the numbers on these rules, we started with rules R0 through R5, and then we weeded out the ones we didn't need. So the R0 rule, the other ones are sound, but we didn't need them. So the R0 rule, the idea here is that if P is not going to be found out before time 5, after X, then the constraint labeled by P, it doesn't make any sense to condition it on the value of P, because you don't know the value of P until you execute P. So this is like a label removal rule. You remove the literal P from the label, because it can't be conditioned just on the value of P when you don't know P. The R3 rule is the tricky one. This is, you know, the idea here is imagine X is at time 0. Now in the scenario where Q and R are true, P is not going to be found out until at least time 3. Well, if you're not going to know the value of P before time 3, then you can remove that P from that constraint on the right, but only up to time 3. So it's considerations like that, and there's other details involved with how you do this constraint propagation and so on, but that's the general flavor. Now, with these Q labels, basically, when you see a P on an edge, basically what it means is if P is known to be true or has not yet been observed, then this constraint has to be satisfied. If you see a not P, it means P is known not to be true or we haven't observed it. If you think about it like that, then these conjunction operation, the expansion of the conjunction operation makes sense, because it's P and not P give you P not yet known, because the original P is known, true, or unknown, and the second one is P is known, false, or unknown. If you can join those two together, you get P is unknown. So that's sort of the intuition behind that. And as far as determining dynamic consistency for CSTNs, we only need to worry about Q-labels on edges pointing at Z, the lower bound constraints. That's what gives us a guarantee that the earliest first strategy will work. So here's what the label propagation rule works, how it works when you've got Q-labels. So notice that the constraint on the left has a Q, the constraint on the right has a not Q. So if in that, imagine if Q is not yet known, then both of those constraints have to be satisfied as long as Q is not known. So that's why you get up there Q question mark. As long as Q is not known, you have to wait at least 8 to execute W, assuming that P and not R are observed. Okay, and that's only for negative values. Interestingly, in the work on dispatchability, which you guys did a long time ago, and Paul Morris did, there were these positive-negative edges. And the positive-negative edges are the ones that you don't do this propagation on. So there's a big difference between the dispatchability, if we can define it for CSTNs, versus STNUs and STNs. And so, you know, we have a similar thing. If you have a P question mark there, you can remove it from there. And, you know, this R3 star rule, QR3 star, that's the R3 star is the generalization of rules R3 and R5. So anyway, so there's some constraints in that. So that's what we propagate these labeled constraints, including Q-label constraints. Now here's an example. And you see the blue loop there is a negative loop. And if you do the QLP rule, you'll find a negative loop with P question mark, Q question mark, R. And we just put in negative infinity there to imagine going around that loop as often as you want. But that doesn't mean the network's not dynamically controllable. This network is dynamically controllable. We can propagate those negative infinities. Basically, if you look at the top edge there, Y going down to Z, one of the labeled values is negative infinity P question mark. What that says is, as long as P is unknown, Y has to wait forever. In other words, Y has to happen after P is known. So it's okay to have those negative infinities, and it's okay to have those Q labels. How do we do DC checking algorithm? Well, we propagate exhaustively using these rules, and we return no if we get any negative loop with a consistent label. So we can do lots of propagation with Q labels, but if we ever find a negative loop with a consistent label, forget it. Otherwise, we return yes. And in the positive cases, we construct the earliest first strategy, and there's something that I call the spreading lemma, which guarantees that the earliest first strategy will work. And although this algorithm is exponential time in the worst case, we've shown it to be practical, and we've got a bunch of benchmarks that are available. So how does the earliest first strategy work? We keep track of the current partial scenario, which I'll call pi. Initially, it's the empty label. We haven't observed anything yet. And after each execution event, we compute the effective lower bound for each as yet unexecuted time point. Now, the effective lower bound depends on the current partial scenario because various lower bound constraints may have labels. And if those labels are applicable with the current partial scenario, you know, if the current partial scenario is PQ and your label is PR, well, that may turn out to be needed. You may need to satisfy that constraint. Until you know that constraint is inapplicable, you have to satisfy it. So the ELB values can be computed for each scenario and each time point. And then you execute the next time point that has the lowest ELB value. So it's the earliest first strategy. And here's how it works. Now, notice the lower bound. We've done the propagation here. And notice that the lower bounds for each one of those time points pointing at Z has a constraint, -7 with the empty label. And that's what the spreading lemma guarantees. It says that if you take the time point that has the smallest effective lower bound, that effective lower bound will spread to the entire rest of all the unexecuted time points with the most general label. So that's where we get the -7. So that means that we can execute one of these time points at time 7. Now notice that P is the one that has the ELB of -7. Y has an ELB of -infinity. And R has a -infinity. And Q has a -infinity. So P is the only one we could execute next in this scenario. We execute it at time 7. Then we notice that Y has an ELB of 7 now. Why is that? Oh, these are light gray. You can't really tell. But the only constraint that's left over, see if P has been observed to be true, all those constraints that have not P or P question mark, they go away. And so Y can be executed at time 7. And same thing for R. By the way, we're assuming instantaneous reactivity here because it's a little easier to present, but you can also do it with non-instantaneous, and you can also do bounded reaction time. So then we execute Y at 7, and then we find out that Y and R at 7, and we find out Q can be executed in 8. However, you can do an alternative execution. Suppose P came out to be false. Then those constraints on the top of Y there, the ones with not P, are still present. So now Y's ELB is 9, and Q's ELB is 7. So you get different results depending on whether P came out to be true or false. So you get different executions, and you can look at those. So there's semantics for the dynamic consistency of CSTNs that have instantaneous reaction, that have non-instantaneous but positive reaction, unbounded, not lower bounded reaction time, any reaction greater than 0, or you have what's called epsilon reaction. So there's some fixed epsilon that you're not allowed to react any faster than epsilon. So Coman and Rizzi introduced that epsilon dynamic controllability, and then we extended our propagation-based algorithm to show that it can be used for epsilon dynamic consistency. So that's nice. If you want to set epsilon to be 10 seconds, it allows you to do whatever computation you need to do in order to react to what you observe. By the way, because in 2009 I found that error in the semantics for STNUs, and they found an error in our 2015 paper, which was almost the same kind of thing, which was, oh, we had made too quick an assumption about instantaneous reactivity, and they corrected that. Fortunately, our algorithm is still sound and complete, but it was a little ironic. Anyway, we all work together. So the idea of dynamic consistency for CSTNs, okay, the theory is good, very solid. There's several competing algorithms, and we're working on comparing them all empirically. We know that the propagation-based algorithm works at least to some degree, but we're going to implement them all and compare them all. And then on flexible execution, we're going to be presenting something later this year about dispatchability. Now, I don't have much time left, and I don't have many slides left. But with CSTNUs, see, in 2012, we presented the semantics of dynamic controllability for CSTNUs, and we presented some sound propagation rules, and that's all fine. And we couldn't figure out how to make them complete. So a couple years later, we decided, well, let's back off that problem and just do CSTNs. And we finally got that to work. The spreading lemma was a key feature of that. And then we finally, after years of effort, finally figured out how to make it sound and complete. And we're going to present that later this year. So that's forthcoming. So CSTNUs, stay tuned. There's more coming. And then what about if you add disjunction? Now disjunction, that's the one that's a killer. Yes, well in 16, Chimati and me and some other researchers from Trento and Verona, we showed how you could convert the DC checking problem for CDTNUs into a controller synthesis problem for a time game automaton. Wow. Okay, that's great. It highlights the relationships between CDTNUs and TGAs. Unfortunately, the algorithm was horrible. Here's a workflow that's got a little disjunction at the beginning, and then it's got those treatments are the contingent links, and then the two diamonds are the the emergency and age greater than 70. Those are the two test actions. And so we've got conditions, we've got uncertainty, we've got disjunction, and here's the TGA. You ready? Get out your binoculars. So although it's possible, you see Agnes and Vera stand for the agent and the environment, and they take turns. And there was a little trick there because the environment can respond instantaneously to Agnes, but Agnes cannot respond instantaneously to the environment. So we had to swap the semantics because the TGA controller algorithm that we were using off the shelf made this assumption, that went the opposite way. So anyway, so the point is they go back and forth, and there's the guards on the transitions that they can do. And then after they're all done, Vera decides to go up there. And if all those constraints are satisfied, then you hit your goal. Otherwise, you fail. And so it's a horribly convoluted thing. And they make all their decisions before you check the constraints. And so it really makes it difficult for the controller synthesis algorithm to find a solution. And so it's just horribly slow. But who knows? Maybe there's a better translation. Don't know. Yeah, a question? No? Conclusions at 2:27. Hey, that's pretty good. So, theoretical foundations for all these kinds of temporal networks is very solid. We did RTEDs, the real-time execution decisions for CSTNUs also in one of our papers. So, we have the semantics is all taken care of. We have good DC checking dispatchability algorithms for STNs and STNUs. CSTNs, the propagation-based algorithm, depending on the application, may be useful. We're doing this empirical evaluation this year and next year. And CSTNUs, we just have this new algorithm, and hopefully that will work well. So, the thing is, this is an exciting area of research because there's lots of problems still yet to take care of. And you can see there's been lots of work that's been ongoing. And I've got all the references there. You can pour over them. So thank you very much. Are there any questions? Yeah?
For robotics, is there any software that allows us to kind of use STN?
Well, the STN algorithms are not hard to implement. So you can implement them yourselves. I've implemented a bunch in Lisp, and I was talking to Brian, and I said, well, the researchers in Verona have done all this stuff in Java, and when we do our empirical evaluations and comparisons, they want me to implement my stuff in Java, and I was saying, he said, do you have any code for us? I said, well, I can give it to you, but it's in Lisp. And he said, yeah, well, that's what we do. So, okay, so, yeah, maybe I can give you some software for STNs and STNUs, and I have implementations for CSTNs, and some initial work on CSTNUs, but I'd probably have to clean them up a little bit before I can give them to you. But yeah, sure.
Yeah, I was just going to ask, are all these strictly online algorithms that you be running, while operating, or can you store the results offline and quantize the space that you get?
Well, it's interesting. It's different for different ones. For the STNU and STNs, you do order n cubed time work before execution. And then for the dispatchability, you do very minimal propagation. I mean, the overall propagation is order n cubed spread over the entire time. So that's not bad, n squared per update. So you do have to do a little work just to propagate. But the idea with the dispatchable network is that there's not that many neighbors. So even though it might be order n squared per execution event, it's probably a small portion of propagation that you have to actually do. So I think there's not a lot of work that you have to do for that. For CSTNs, all the work is done by the spreading limit in advance. It's exponential, but during propagation, all you have to keep track of are which time points are enabled and throw away the constraints that are no longer, okay, well, you have to throw them away. So I guess that takes some work because there could be an exponential number of constraints.
Yeah, what I was thinking was, if you could learn how the space is related amongst those different particular states that you have, maybe you can run a little faster.
Yeah, I mean, in the work on TGAs, there are, when they say controller synthesis, the TGA work presents this, it's a very complicated controller, but it can just be put into hardware and just run it. So if you can do that for TGAs, you can probably do it for any kind of temporal network. Other questions? All right, well, thank you very much. This talk is online. All my papers are online, so please have a look. And don't forget, if you're interested in collaboration amongst multiple agents, we have some papers there that might be of interest to you.
So just one quick comment. So we're going to have half an hour coffee break. So then we're going to have an intro for the lab here. So don't go around, just stay around here. And then 20 minutes after this intro, we're going to go all together downstairs. We're going to basically do the lab. That goes up